Hello everyone. So in this video I am going to talk about minimizing finite states. We are still talking about the properties for regular languages. So why we care about minimizing finite state machines? Remember this NFA, which was a part of the examples that we checked when we talked about the finite automaton? This NFA is going to accept all binary strings containing the pattern 0, 1, 0. If I create the equivalent DFA for this NFA, I usually actually come up with a DFA with a lot of states. In general, not only converting NFAs, but also converting regular expressions, the algorithms that we have seen for them, there's a good chance they will create a lot of states that we don't really need all of those states. So at the end, the equivalent DFA that we have is going to have a lot of states that many of them can be removed. That's why we are going to talk about minimizing the number of states in a DFA. And interestingly, there is some algorithms, actually there are two different algorithms that they can minimize the number of states in a DFA, and for each regular languages actually there is a unique DFA with minimum number of states. So all the algorithms are going to give, if you give the different DFAs, all of them for the same language, the output of the algorithm for all of those DFAs are going to be unique. It's going to give you a unique DFA, which is the minimum size DFA for your language. So today I'm going to focus on these algorithms, see that if we have a DFA, how we can minimize the states. So if you look at this example, the DFA for this language that actually accepts all the binary strings that have the pattern 0, 1, 0, one thing that is clear here is about these final states that I have. Q3, Q4, and Q5, all of them are accepting states. And in fact, when you reach to one of them, when you reach to Q3, you are going to stay in these final states. You are not going to go anywhere else, right? From Q3, if you see 0, you will go to Q3. If you see 1, you go to Q4. If you in Q4, if you see 0, you are going to go back to Q3. From Q4, you go to Q5. In Q5, you stay or go to Q3. If you reach to a final state here, you are going to stay. So all of these, the behavior of all of these final states that I have here are going to be the same. So basically, it is very clear that I can merge them. Instead of having 3 different accepting states, I can merge all of them and have an equivalent DFA like the one that I have in the bottom, that in fact all of these 3 states have been collapsed and have been actually merged to only one state. When you reach to this final state, you will stay at this final state. So the idea of minimizing the DFAs is exactly coming from this idea that we try to find all of those states that can be merged. When we are minimizing a finite state, we should be very careful about one fact. The resulting of minimization is going to accept exactly the same. You are not going to accept any more strings or reject some strings that you are accepting in the original one. So for minimizing any finite states, we have two different steps. The first step is to get rid of all the inaccessible states. So if there are some states in your finite state that you cannot reach to them from the starting state, we call them inaccessible states. If I wanted to give you an example, look at this finite state, finite automata, that this is going to be the starting state. From this one, for example, over 0, you go here. There are some states here that you actually can reach to this one or this one by 0, 1. Another state, for example, with 0 stay here, with 1 you go here, with 0. I'm just drawing it on the fly. In fact, it's not going to show something specific. Okay, if you look at this DFA, let me actually give some name to these states. A, B, C, D, and E. If you look at this finite state, you can see that E is in fact E is an inaccessible state. Why? Because if you start from the starting state, let's actually have another transition that from A it goes to 1. With 1 from A you go to A. From the starting state, there is no chance that you can reach to the state E. So all of the inaccessible states that you have, you can simply just get rid of them. They are not going to play any role in accepting or rejecting any string, because you cannot reach to them from the starting state. You might actually just ask why I have this inaccessible state. In fact, when you are converting the states, remember we have talked about the closure properties. If you just follow some of those algorithms to create a finite state, in some cases you definitely will create some states in your finite state which are not accessible from the starting state. So it is possible to create some states which are not accessible. And so the first step in minimizing the state in a DFA is to get rid of the inaccessible states. And how we can do it? We can simply just think about your finite state as a graph and run a DFA or, a depth first search or a breadth first search. Both of them is going to work, and both of them are going to have the same time complexity. Starting from the starting state, if you run a depth first search or a breadth first search, the algorithms are going to visit all accessible nodes from the starting point. And all those states that you don't visit them after, if you haven't visited them after the breadth first search or depth first search, they are inaccessible and you can simply just remove them. So this is the first step. The second step is to try to find those states which are indistinguishable, or we call them equivalent states. If you have two states that, or two or even more than that, those states can be, if they are equivalent, they can be collapsed, they can be merged together. And instead of, you can just have one state instead of all of them. An example of that is exactly this case, that all these states Q3, Q4, and Q5, they are all equivalent, indistinguishable. So we merge them and just have one state in the final minimized Dfa. Okay, so how we can actually recognize indistinguishable state? This is the question. This is something that I'm going to focus on. I'm going to show it to you using a couple of examples just to give you the intuition first. Then we will discuss the algorithm in details. So look at this DFA. If you look at this finite automaton, you can see that clearly it is going to accept the language with only two strings, 0 or 1. With 0 it goes to an accepting state, with 1 it goes to an accepting state, but after that if you see anything else it goes to a dead state, Q3, and it will stay there. It will never go back to the accepting state. So this finite automaton is going to accept the string with two, a language with two strings, 0 and 1. So if you look at the states here, something is clear about these two states, Q1 and Q2. If I am at Q1, I'm in an accepting state. If I'm at Q2, I am in an accepting state. So one thing that I know about these two states is both of them are accepting state. I cannot, for example, combine two states that one of them is accepting, the other one is rejecting. So for example, Q3 cannot be merged with Q1, or Q0 cannot be merged with Q1, or Q0 cannot be merged with Q2, because one of them is accepting, one of them is rejecting. So when I'm actually talking about merging them, I am just considering all either accepting state or all non-accepting states. So Q1 and Q2, the first thing is marked, both of them are accepting, good. The second thing is that what would happen, how they are going to behave if I am at Q1 and if I see 0. How, what will be the behavior of the finite state if I am at Q2 and I see 0? I should consider all of it for all possible tokens, all possible input tokens that I have. As you can see from Q1, by seeing a 0, I'm going to Q3. At Q2 again, by seeing a 0, I'm going to, Q3. And from Q2, by seeing a 0, I'm going to Q3 as well. So far, their behavior is similar. I still need to check another actually thing. From Q1 with a transition over 1, I'm going to Q3. From Q2 with a transition over 1, again, I'm going to Q3. So that's it. The behavior of Q2 and Q1 are the same. They can be merged. Both of them are accepting. And if you are at either of them, by seeing 0 or 1, both of them are going to Q3, which is a dead state, and that's it. Q1 and Q2 are going to be merged. They are indistinguishable. They are equivalent. Look at another example. This finite automaton is going to accept all binary strings which are either 0 or 1, or at least have length 3. Okay, so as you can see, over 0 or 1, it goes to Q1 and Q2, both of them accepting. And from Q1, if you see anything else, with 0, it goes to Q3. With another token, it goes to Q5. Or from Q2, it actually needs to go to 0 or 1, and at the end actually end up to Q5. So this is going to be the language of this automaton. So I'm going to check which states here are going to be indistinguishable. The potential pairs that they can be merged together are going to be Q1 and Q2, And also I can actually consider the Q1 and Q5, but let's actually first look at these pairs. Or another pair that is potential is Q3 or Q4. If I look at Q1 and Q2, they are both accepting. So far their behavior is the same and it is good. But with Q1, with 0, from Q1 with 0, I'm going to Q3. And from Q1 with 1, I'm going to Q4. With Q2, everything is different. With 1, it is going to Q3. And with 0, it goes to Q4. So the behavior of Q1 and Q2 they actually looks different. So I cannot merge them here. So let's look at another pair, Q3 and Q4. Both of them are non-accepting, right? If I am at Q3, if I see 0, 1, 0, for example, from Q3 over a 0, I'm going to Q5. From Q4 over a 0, I'm going to Q5 again. So far again, good. From Q3 over a 1 transition, I'm going to Q5. And over Q4, with 1 transition, the transition over 1, I'm going to Q5 again. So the behavior of Q3 and Q4 is completely the same. I can merge Q4 and Q3. So after I merged Q4 and Q3, the DFA would look like this. From Q0 Q1, Q2, I'm going to just give the same name here. The combination of these two to make it clear. That when you see that when I'm actually collapsing, merging the Q3 and Q4, Q1 over 0 and 1, both of them are going to go to the same state, and Q2 over 0 and 1, both of them are going to the same state. And from here, over 0 or 1, it is going to an accepting state Q5. Okay? So now in the new DFA that I have, it is clear that Q1 and Q2 are equivalent. They are both accepting a state, and with the transition over 0, both of them are going to the same state. With transition over 1, both of them are going to the same state. So that's it. I can actually merge both of them, and the result is going to be this DFA. And I can see that I cannot actually, for example, combine more states here. This state Q1 and Q2 cannot be merged with this state Q5, right? Because from Q1, Q2, you are going to a non-accepting state by seeing a 0, 1, but from Q5, you are going to an accepting state. And a non-accepting and accepting state is clearly cannot be merged together. Okay, but what I explained to you is not really, a coherent algorithm. It is just like I'm going on fly. I'm just checking each pair. And I don't know, for example, at first when I was checking Q1 and Q2, they are not equivalent, right? But after I checked Q3 and Q4, then I noticed that, yes, I can actually convert Q1, combine Q1 and Q2 as well. So it's like some procedure that you have to do a lot of search and you have to redo some of these checks, right? So this algorithm is not a coherent algorithm. I need a coherent algorithm, something that that is more efficient in terms of checking these pairs that can be combined together. I'm going to show you that algorithm. It is just, I wanted to give you the intuition over these examples. Okay, let's see another example here. Again, here you can see that the states, for example, Q3 and Q4 are going to be indistinguishable because both of them are going to be accepting and both of them are going to go to another accepting state over both transitions 0 and 1. And after you actually merge them, you can also merge them with Q5, right? So basically all these three can be actually combined together. And after you combine them, you can also merge the two states Q1 and Q2 as well. So everything in these different examples was about you take a pair, you check the behavior of this pair, that are both of them accepting or non-accepting, and what would happen if I am at both of these two states. If I am at state 1, what would happen if I see, for example, the transition 1? If I see the transition over 0, what would happen to the other states? So I'm just checking all the possible behaviors over these states. Let's see another example. What do you think about these DFAs? As you can see, the left one is going to accept this language. It is going to accept all strings of 0 that the length, the remainder of the length over 3 is going to be 1. So all the strings like 1 0 or 4 0 or 7 0 or all these actually strings, the length of the string mod 3 is going to be equal to 1, right? From Q0 you go to an accepting state by seeing a 0. By seeing 3 zeros, it's just actually moving until it goes to another accepting state. The thing is, these two DFAs that you can see here, they are both equivalent. They are both going to accept the same language. And as I have actually marked here, Q0 and Q5, all of these pairs, in fact, are going to be equivalent. Q0 and Q5 are equivalent. Q1 and Q4 are equivalent. Q2 and Q3 are equivalent. But the previous approach that I took is not going to work here. If I take any pair here, for example, Q1 and Q4, if I look at the behavior of Q1 and Q4, both of them are non-accepting. It is good. But what would happen from Q1 over a transition 0? It goes to Q0. And from Q4 over the transition of 0, you are going to Q5. It looks like they have a different behaviors, right? So I cannot combine them, merge them. Another pair that I might actually check is, okay, let's check Q, for example, Q0 and Q5. At Q0, the transition over 0, I am going to Q2. From Q5, with the transition over 0, I am going to Q3. Again, as you can see, they are not going to end up to the same state, so I cannot convert them. Let's check another pair. For example, Q2 and Q3. Both of them are accepting states, so far good, but let's check what would happen over different transitions. I only have transition over 0, so I will check that. From Q2 over the transition of 0, I am going to Q4. From Q3 over the transition of 0, I am going to Q1. Again, I don't know anything about the pair Q4 and Q. I mean, I don't know if they are equivalent or not, right? So you can see that if I go actually over and over all these pairs, I cannot really get anything. But I know that in fact all of these pairs are equivalent. Q4 and Q1 are equivalent, Q0 and Q5 are equivalent, and Q2 and Q3 are equivalent. From these actually checks that I have done here, I can in fact extract something. I can recognize something from this exploration that I have done over these pairs. That if you have pair Q1, Q4, if you wanted to actually just check if they are equivalent or no, this pair is actually depending. This is not a finite state. I'm not trying to create a finite state here. This pair is going to depend on the equivalency of Q0 and Q5, right? So as you can see, Q1 and Q4 here, they are going to depend on this pair Q0 and Q5. The equivalency, and another thing that you actually can see here is that the equivalency of this pair is going to depend on equivalency of this pair. See these actually green things, edges that I am actually drawing is the dependency. And the dependency of this pair is going to depend on, the equivalency of this pair Q2 and Q3 is going to depend on another pair Q1 and Q4. Okay? So, in fact, as you can see, all these pairs which are actually equivalent, they are going to depend on each other. This is exactly the basis of the algorithm that I wanted to show you. Before showing you the complete algorithm, I want to define the indistinguishable state more formally. I'm going to actually give you a complete definition for that. So one fact that we know about the states in a deterministic finite automaton is that if a state is accepting and another state is non-accepting, they cannot be merged together. They are distinguishable. Okay? So inductively, we can expand this definition and say that we cannot collapse, we cannot merge two states P and Q if we know that over some strings from P you reach to a final state, and from Q over the same string you reach to a non-final state, or vice versa. Okay, from Q you reach to an accepting state, from P you reach a non-accepting state. So now I can define the indistinguishable state. I can give you a formal definition for indistinguishable states. We would call P and Q indistinguishable or equivalent, and we show it actually using this math term. If and only if this is exactly the definition, that for every possible string if you start from P and see that a string X, if you reach to a final state, then from a state Q, by visiting that string, by reading that the same string, you also reach to a final state. And as you can see, this is the if and only if term. So it means that if from Q, you, by reading any string, you reach to an accepting state, the same string from P also will result to a final, an accepting state. And actually, if you reach to a non-accepting state, it should also reach to a non-accepting state on the other state. This definition is in fact an equivalence relationship. So if you find two states which are equivalent, for example, P and Q, they are equivalent, and you also find out that Q is equivalent with another state like R, then P and R are also equivalent. So all of them are going to be equivalent to each other. And this relationship is equivalent, so basically it has all of the three properties of equivalence relationships: the reflexive, symmetric, and transitive. So if P is equivalent to Q, Q is also equivalent to P. If both one state is definitely equivalent to itself, and that transitive property, that if P is equivalent to Q, if you showed P is equivalent to Q, and you also showed Q is equivalent to R, P is also equivalent to R. So this is the formal definition of indistinguishable or equivalent states. I'm going to, in fact, use just this definition to write down my algorithm. I'm going to run that algorithm by, instead of actually giving the complete algorithm to you, I'm going to run it over a couple of examples. I think this is going to be easier to understand. The complete algorithm is going to be available in your textbook, so I'm going to just run it over a couple of examples here, but it covers all the details, don't worry. So let's look at this example, the last example that we have seen. This is a DFA. We wanted to actually minimize it. One thing about, I probably need to add this one here, that we know the alphabet is going to be only one character, 0. Okay, in this algorithm, I'm going to check all possible pairs that I have, all possible pair of states that I have. So if I have n states in my DFA, the total number of pairs, potential pairs that I have to check is going to be n to n minus 1 divided by 2 different pairs. To have a coherent actual analysis over all these pairs, I'm going to create a table showing all these possible pairs. You can see that I have a table here. If each row and column is going to correspond to one state. And for each row, I'm showing you all potential other states that can be equivalent to each state. For example, for Q0, Q5, Q4, Q3, Q1, and Q2, and Q1. And as you can see, I'm not actually showing, for example, another column for Q0 and Q0, Q0 and Q0. They are equivalent, or they are the same. So it doesn't really matter how you are showing this table. I am just deleting all those the cells corresponding to pairs that we are not really interested in. We don't want to check them. This is going to cover all the possible cases that we care about. So after drawing the table, the first step is to just put all the information that we have. The very first thing that we know is all those states which are accepting, they are not going to be distinguishable, they are not going to be indistinguishable or equivalent with those which are not accepting a state. So I'm going to show this information here in the table. that Q2 is not going to be equivalent to Q4, Q5, Q0, and Q5, Q1. Okay, so all those cells are going to be, okay, Q2 is not going to be equivalent to Q5, to Q4, to for Q4, it's not going to be equivalent to Q0, it's not going to be equivalent to, what else, Q4, Q5, and Q2, Q0, and Q1, okay? Also for Q3, it is not going to be equivalent to Q0, it's not going to be equivalent to Q1, it is not going to be equivalent to Q5, and it is not going to be equivalent to Q4. So these are all the facts that I know at the very first step. I marked all of them in the table. The rest of it is going to be those pairs that it is possible that they can be equivalent, right? I need to actually check them one by one. How I am going to check these cells? I am going to do it in a, more organized way. I will start from the first row, go down, and in each row I am going to do it from left to right. So the very first, actually it doesn't really matter, I'm just going to give you a more organized way. We are writing an algorithm, right? Be careful about it, so everything should be organized in some way. So the very first pair that we are checking is going to be Q0 and Q5. You should check all the behaviors for these states. So in this case, the alphabet is going to have just one character, so only one transition is going to be checked. From Q0 over 0, I am going to Q2. And from Q5 over 0, I am going to Q3. Right? So now I know something about Q0 and Q5. That the equivalency of these two states is going to depend on equivalency of Q2 and Q3. When I'm checking that, I first need to actually refer to the table. Refer to the corresponding cell in the table, Q2 and Q3. Basically, so far I know nothing about Q2 and Q3, right? So I still can't decide about Q0 and Q5. But I just know that they are going to depend on this cell. This is something, you can see that I am still checking, this cell, right? I haven't reached to this cell yet. So to just make sure that I keep this information that so far I have learned, because I haven't reached to this cell, to the cell Q2 and Q3 yet. So I'm going to just keep this information, this dependency, the dependency of Q0 and Q5 to Q2, Q3. I'm going to actually keep this dependency somewhere. Where to keep it? The easiest way is to just write it down simply here in this cell. Okay, so whenever I will actually see something, some dependency, now I know that, okay, whenever I decided about Q2 and Q3, I will also can decide about all those pairs that depend on Q2 and Q3. So far I will let it go, and I have actually just stored all these dependencies somewhere. So let me just do some cleanup here. Okay, so we are done with the first cell. The next cell that I'm checking is going to be the pair Q0 and Q4. Over the transition of 0 from Q0, I'm going to Q2. From Q4 over the same transition, I'm going to Q5. So the equivalency of this pair Q0 and Q5 is going to depend on the cell Q2 and Q5. I am going to refer to the table, and so far I already know Q2 and Q5 are distinguishable. They are not equivalent. So of course Q0 and Q4 cannot be equivalent as well. I'm going to just update the table and mark this cell. Let's do a cleanup. The next pair that I'm going to check is going to be this cell, the last cell of the first row, Q0 and Q1. From Q0 over the transition of 0, I'm going to Q2. And from Q1 over the transition of 0, I am going to Q0. So this cell, this pair is going to depend on the pair Q2 and Q0. Do I know anything about Q2 and Q0? Let's just refer to the table. Yes, I already marked them as not equivalent pair. So I can simply just mark this one as not equivalent as well. I have decided about it. That's it. Let's just do some cleanup here. Okay, I'm done with the first row. The second row, the first cell is going to be Q1 and Q5. From Q1 over 0, you are going to Q0. From Q5 over 0, you are going to Q3. So the equivalency of the pair Q1, Q5 is going to depend on Q0 and Q3. Do I know anything about that? Let's refer to the table, Q0 and Q3. Yes, this cell has already marked as not equivalent or distinguishable pair. So I can just fill the table and say that they are not equivalent. The next pair is going to be Q1, Q4. Q1, Q4. Over the transition of 0 from Q1, you go to Q0. From Q4, over the same transition, you go to Q5. Okay, so now I have seen something. The equivalency of this pair Q1, Q4 is going to depend on the equivalency of Q0 and Q5. So if I'm going to do the same thing here, I have to go back and write the dependency of Q1 and Q4 in the same cell here, Q1, Q4. Okay, so whenever I decided about Q0 and Q5, I can also decide about Q1 and Q4 as well. So now you can see that the equivalency of Q1 and Q4 is going to depend on that cell. So I'm going to leave this cell of Q1 and Q4 yet because I haven't decided about Q0 and Q5. So let's go to the next row. Let me just do it. Let me just erase this here. The next cell is going to be Q2 and Q3. Okay, this cell here. From Q2 over 0, you are going to Q1. From Q3 over 0, you are going to, from Q2 over 0, you are going to Q4. And from Q3 over 0, you are going to Q1. Okay, so the equivalency of this pair is also going to be depend on the other pair Q1 and Q4. So I'm going to just write it down here. Okay, so one thing that so far you have learned is that I am actually creating that loop of dependency, that the equivalency of Q0, Q5 is going to be depend on Q2, Q3, Q2, Q3 is going to depend on Q1, Q4, and Q1, Q4 is going to depend on Q0 and Q5. Okay, so let me actually just leave this cell here. I have actually written that dependency in the corresponding cell, and I'm going to just go and finish all the cells in the table. The only cell that remains here is going to be this one now, Q4 and Q5. Q4 over 0 is going to Q5, but Q5 over 0 is going to Q3. So the equivalency of this pair is going to depend on the pair Q5 and Q3. I'm going to refer to the table Q5 and Q3. This is already marked as distinguishable or not equivalent. So that's it. I know that this pair is going to be not equivalent. So let me just erase all of this and see that I'm done with filling the table. Let's see that what we know and what we can actually just understand from the rest. So all those pairs that we immediately know they are not going to be equivalent has been marked. There are just a couple of cells that we haven't marked them, and they are basically showing some dependencies that a pair Q1, Q2, this is not, I'm not drawing a finite state, I'm just drawing some dependencies. This pair is going to be, the pair Q1 and Q4, Q1 and Q4 is going to depend on the equivalency of Q2, the equivalency of Q0, Q5. The equivalency of this pair is going to depend on the equivalency of Q2 and Q3, and the equivalency of Q2 and Q3 is going to depend on Q1 and Q4. Okay, I have actually created a loop of dependencies, but I don't need to actually do more investigation. That's enough. All of these potential pairs are going to be equivalent because I have this loop and everything is fine. In fact, Q1 and Q4 is distinguishable. They are going to be the same. They are equivalent. Q2 and Q3 are equivalent. Q0 and Q5 are going to be equivalent. At the end of the table, if you just after you finish checking all the cells, if you end up with some cells that hasn't been actually filled, they are just going to be a couple of dependencies between these pairs. You can just take all those pairs, all those potential pairs as the equivalent pairs. So Q1, Q4 are equivalent, Q2, Q3 are equivalent, Q0 and Q5 are equivalent. And I'm done with the table. I'm done with this algorithm. The only thing that I should do here is to just rewrite the DFA. So I'm going to create a new DFA, one state for Q0 and Q5, and it is going to be the starting state for you over 0. You can see that if you check it over 0, they are going to, Q0 is going to Q2, Q5 is going to Q3, and they are equivalent. So you are going to the same, to one state here, which is accepting state. And from Q2, Q3, over the transition of 0, you are going to another state, Q1, Q4. And from Q1, Q4, you are going to, over transition 0, you are going to another state, Q0, Q5. And this is going to be the final DFA for this, final minimized DFA for this original DFA that we got. Okay, let me show it to you over another example. Again, how many states I have here? I have 6 states. I will draw the table, one row for each table and corresponding actually columns for the corresponding cells. The first step that I do is going to mark all those states which I directly know they are not going to be equivalent. For example, E and all of the non-equivalent states, F and all of the non-equivalent states, they are not going to be equivalent. So I marked all of them in the table first. Then I will start it from the first row, from left to right, check each cell one by one, and just check them to see if they are equivalent or no. And I will check all the possible transitions. Here, the alphabet is going to be 0, 1. So for each state, I have to check two different transitions. And in this example, along the way that I'm filling the table, I'm showing you some dependency graph as well. This graph that the previous graph, I've actually erased it, so forget about that. I'm going to show you that dependency graph. I'm going to create that dependency graph as I'm filling the table as well. It is probably just making it more easier to understand. At least I think so. Okay, the first cell to check is the pair A and D. For A, I will check that what would happen if I see a 0. And for D, what would happen if I see a 0? From A over a 0, I'm going to B. Let me use a different color. From A over a 0, I am going to B. From D over a 0, I am going to the same state D. Right? So here, the equivalency of A and D is going to be depend on another pair, B and D. Not only that, I've also actually checked that over the transition of 1 from A, you are going to C, and from D, you are going to actually stay here. So the equivalency of A and D also will depend on another pair CD. So as you can see in the dependency graph, I am actually drawing some dependency for AD from AD to both BD and CD. So if AD is going to be equivalent, B and D should be equivalent, and C and D, both of these two pairs should be equivalent. So far I can get nothing more from this for this pair. So I'm done with this with this cell. One more thing, I just forgot that we have to update. We have to write down these dependencies somewhere, right? I'm going to actually write them down in the cells, in the corresponding cell of BD. I am writing down that dependency of AD. So it's just telling me that whenever I have checked the equivalency of BD, whenever I decided about that, I will also decide about AD. The same for this pair as well. Whenever I know about the C and D, I will also go and actually update the cell for AD. The next cell to check is A and C. So what I need to check is that from A, with the transition of 0, you are going to B, right? And from C, over the transition of 0, you are going to F. So one thing that I know here is that A and C is going to depend on the pair B and F. If you check the corresponding cell here, B and F, I already know that they are not going to be equivalent, basically because one of them is accepting, the other one is not accepting. And that's enough. I don't even need to check the other transition for A and C. That's enough to know that AC is not going to be equivalent, and I am marking it in the cell as well. And you can see that in the dependency graph, I have actually just update this pair as well. So I'm done with this cell. The next cell is going to be in the first row, the last column, A and B. The equivalency of A and B is going to depend on over the transitions, right? From A with 0, you are going to go to B. From B over 0, you are going to E. So the equivalency of A and B is going to depend on depend on this pair, right? And also depend on another pair over the transition of 1, but I don't care about this one anymore, because I already, from this dependency, I know that they are not going to be equivalent. If you check the corresponding cell for B and E, I already know that we have marked it as not equivalent. So that's it. I don't even need to check the other transition. B and A and B are not going to be equivalent. So I have marked them as not equivalent here. The next cell to check is going to be B and D. So this is the cell that I'm checking, and you can see that I already know one dependency over that. That if I learned about B and D, I can also update the corresponding cell for A and D as well. But let's just check B and D first. So from B over 0, I am going to E. From D over 0, you are going to stay at D, right? So the equivalency of this pair B and D is going to be depend on the equivalency of the other pair E and D. If you check the corresponding cell, you can already see that E and D are not going to be equivalent. I don't need to check the other actually transition, although the other transition is going to be B over 1 is going to D, and D over 1 is to the same. So the other transition is good, but this transition is making B and D not equivalent. So that's it. I know that B and D are not going to be equivalent. Not only I am going to mark B and D as not equivalent, but also anything that will depend on this pair is going to be not equivalent as well. So it's just like a backtracking for you check all those pairs that will depend on B and D. For me, I know that there is another pair, A and D, that is depending on B and D, I will go and mark that state as those pair, that cell, as not equivalent as well. Okay, so I'm done with this cell and I have actually filled all of the dependencies for that one as well. So the next cell to check is going to be this cell here corresponding to B and C. If you check the transition of B and C, B over 0 is going to E and C over 0 is going to F. So I already know that the equivalency of B and C are going to depend on E and F. Do I know anything about E and F so far? I don't know anything. So I haven't actually reached to this cell yet. I'm still in the upper, in the second row. So I don't still know about this, but I can just go and write down that dependency here, right? So I need to keep these dependencies that I have learned, that the equivalency of B and C is going to depend on E and F. And whenever I learned about E and F, I will just go and update the B and C as well. So the other transition of B and C is going to go over 1. Both of them over 1 is going to D. So I know that they are going to go to the same state. So this is the only dependency for B and C. I'm done with checking this cell. The next cell to check is the state, the cell C and D. Okay, for this pair, for C, over the transition of 0, it goes to F. For D, over the transition of 0, it goes to itself. So far I know that the equivalency of C and D is going to depend on the equivalency of D and F. Do I know anything about this one from the table? Yes, I know that they are not going to be equivalent. They are marked as not equivalent yet. So that's enough. I know that this pair, this cell, is going to be marked as not equivalent. Whenever you actually just check that they are not equivalent, you also need to update all of their dependencies as well. So the corresponding cell A and D will be also marked. So if it was not marked before, no, we would mark it as not equivalent, but it has already been updated. Anyway, it's not going to change anything for me. And the last cell to check is here in the last row, E and F. Let's see that what would happen over different transitions. From E, over the transition of 0, you are going to E. And from F, over the transition of 0, you are going to F. And over the transition of 1, you are going to, from E, you are going to go to E, and from F, you are going to go to F. So as you can see, E and F are going to depend on themselves. So it's a kind of a loop in your dependencies. And that's it. I don't need to check anything else. They are equivalent. I'm done with the table. I have checked all of the cells, and all those cells that haven't been marked, I can just fill them. So far, I know that E and F are going to be equivalent. So the other pair that depends on them, B and C, they are going to be equivalent as well. So in this case, what I will learn is that the pair B and C are equivalent, and the other pair E and F are equivalent. I can draw the equivalent minimized Dfa in this way, that from A, with the transition of 0 or 1, you go to the same state, which is just the merging of B and C. And from B and C, by seeing a 0, you go to another state, which is the merge of E and F. And over the transition of 1, you are going to another state D, which is basically a dead state as well for us. But it's just, accidentally happened to call it D. I didn't meant to call it D. Anyway, this is done. This is the full actual algorithm that I have. But before finishing the discussion here, I would like to just discuss about the time complexity of this algorithm. As you can see, what I just showed you, although it was over an example, you can simply just write down the full algorithm. That if I pass you as the input as the table transition for the DFA, you can simply just write down an algorithm, write a code for that to minimize the number of states. So what will be the time complexity of this algorithm? If you basically think about what I'm doing in this algorithm, I fill this table. So the whole computation is just what I am doing to fill the table. The first thing is that how many cells you have in the table. The number of cells that you have in the table is going to be n2 n minus 1 divided by 2, right? The number of all possible pairs that I have. And how many computation I need to fill each cell. All those cells that corresponding to pairs that one of them is accepting and the other one is non-accepting can be done with a constant amount of work, right? You just check for each accepting and non-accepting pair, you just mark them. And for the rest of the cell, what you do is just for each cell, you check all the transitions, right? And nothing more. For each cell, you are just checking all the transitions. So whatever is the size of your alphabet, it is going to be how much computation you actually need for each cell. So in total, this is going to be the time complexity that I can basically, because the size of your alphabet is going to be something finite, I will consider it as a constant. So the result is going to be O of n power 2. You might also actually ask that for some of the cells, there might be some dependencies and you are going to follow these dependencies. But at most, we are going to have exactly n to n minus 1 divided by 2 different pairs. So at most, you are going to have this many dependencies to check. So in total, it is going to be still n square, the time complexity of the algorithm. I've just written all of this for you in the slides. Here, just one more note, the dependency graph that I showed here, this dependency graph, you don't really need to draw it. I just drew it here to just, make it more easy to understand what would happen. So before I finish this video, I'm going to, the algorithm that I showed you is the algorithm from the textbook. I'm going to show you another algorithm because I actually found it somewhere else and I found it very interesting. So I thought that it's really fun to just discuss this algorithm as well. What I'm going to do for this algorithm is, at the very first, I will create 2 different groups. I will put all of those non-accepting states in one group and all of the accepting states in one group. So far, I know that if a state is accepting and another state is non-accepting, definitely they are not going to be equivalent, right? But still there is a potentiality, it is possible that maybe all of these non-accepting states are going to be this equivalent, and all the accepting states are going to be equivalent. I will start it with two groups, and I will check the transition over all of the states, and each time I try to actually just whenever I notice a different behaviors, I will create more groups. I will split each group to more and more groups until I'm not actually changing anything. So the first thing to check is that, okay, so that's why you can see that here in this table that I draw, I have two groups. I am showing all the states in each group, and I am drawing some columns corresponding to all possible inputs. So here the alphabet is binary, so that's why I just have two columns, 0 and 1. So I'm going to just check what would happen to each state over each transition. From A, I know that over the transition of 0, I'm going to a state B. Because B is still in the same group, so far the current group that I am in, instead of writing it down as a complete thing, I just make it as, I'm writing it in this way, that okay, I am staying, if I am in the group, in this group at state A, I am staying in the same group. I'm going to B is still in the same group, so I'm just writing it in this way. Over 1, I will also stay in the same group, right? Because I'm going to C. With B, if I see the transition, if you look at the transition, over 0, you are going to a different group. So that's why I'm actually writing it as E. But over 1, you are staying in the same group. Over 1, you are going to D. It is in the same group, so I'm just writing it as it is, you are staying in the same group. Let's look at the C. The behavior of C is that over 0, I am going to F, which is in a different group, and over 1, I'm going to D, which is in the same group. Okay, let's just finish all of the states. For D, if you see a 0, you are going to stay in the same group. If you see a 1, you are going to stay in the same group. So I'm done with this, the first group. Let's check the second group. From E, with seeing a 0 or 1, you are going to stay in the same group, right? You are actually staying at E, which is in the same group, in the group that you have E. So you are going to stay. And for F, you are going to actually stay in the same group. So I'm done with filling the whole table here. What I have learned here is that this group, the behavior of it for all of the rows is going to be the same. So I'm not going to touch this. But how about this group? As you can see, there are some states that they are referring to, for example, for A and D, the behavior is the same. But I have some issue here. These two rows, B and C, they are going to have a different behavior than the rest of the group, right? B over 0 is going to go to the different group. C is going to go to a different group, but they are going to the same group, right? Both of them are going to go to the same group. So I'm going to split this group and actually create two different groups for this one. A and D, B and C, and I'm not touching E and F. So again, because I have changed something in the table, because I have splitted some group, so I need to I need to check the behavior of all the states again. So for A, if you go over 0, you actually go to B, right? And if you go over 1, you are going to C. Both of them are going to actually to the same group, but anyway, they are not staying in this group here. But for D, you can see that over 0 and 1, both of them, you are going to the same group. So again, I'm seeing some differences between behavior, but let's actually just keep that. I'm going to fill out the whole table, then check to see that which groups can be divided. Can be splitted more. So now I'm going to check for B and D. As you can see, for B, over the transition of 0, you are going to this group. And with C, over the transition of 0, you are again going to the same group. With the transition of 1, you are going to the same group, to the other group, but you are going to actually do the same group. And for E and F, you are going to stay in that group. So one thing that I learned here is that I don't need to split E and F, and I also don't need to split B and C, because the behavior is the same. Over 0, both of them are going to go to this group, and over 1, both of them are going to go to this group. But there is something happening for this group here. The behavior of A and D are different, so I need to split that group again. Because there is a change in the table, I have to again fill out the whole table. If I fill out the whole table, I can see that, okay, those groups that have only one state, you don't need to be worried about them. You cannot split them more, right? So you check the rest of the groups. B over 0, it goes to this group. C over 0, it goes to this group. B over 1, it goes to this group. C over 1, it goes to this group. So the behavior of them is the same. For E and F also, you have the same behavior. They are going to stay in the same group. And that's it. I reached to the point that I'm not changing anything. I don't need to split any group anymore. So whenever you reach to this point, you will stop. So all of those states which are in the same group, they are going to be equivalent. So E and F are equivalent, B and C are equivalent, D is one state and A is one state. Each of these, in fact, groups is going to represent one state in the final algorithm. One interesting about this algorithm is that the way that I explained it here, the time complexity is still going to be O of n power 2. Okay? Because you have n number of states. At the first, you are going to create two different states, but two different groups, possible groups, but you are going to break them down. And it is possible that you break them down until you reach n different groups. That's why the time complexity, the way that I actually do it here is going to be n power 2. But an interesting thing about this algorithm is that the time complexity of the second algorithm can be modified. You can modify the algorithm. You can make it better and reach to O of n log n. This is the good thing about the second algorithm. This is something that makes it more fun than the first one. About the first algorithm, that is O of n power 2, is the best thing that you can get, because you are filling the table. The number of cells in the table is O of n square. You cannot get anything better than that for the first algorithm. Think about it, that how to modify the second algorithm to get to n log n. This is a very interesting actually problem. I'm done with this lecture for minimizing the number of states in a DFA. Again, I'm emphasizing that for any languages, you can create a unique DFA with the minimum number of states. So if you have many different DFAs for the same language, if you minimize all of them are going to end up to be the same DFA, although they might actually look different because the name of the states would be different or something, but all of them will be the same. They are going to be a unique DFA with the minimum number of states for that language. But this is not the case for the NFAs. Be careful. There is an interesting example for this one in your textbook, but you can easily think of some example for this. In the case of NFA, you can, for the same language where you can create two different NFAs with the minimum number of states, and they are different, actually. So this is just the property of the DFA, that the minimum number of states will cause a DFA, a unique DFA. For you, I have actually added two other examples. One of them that I've shown the full steps, and the other one just keep it as an exercise. That's it for this video. This is going to be the chapter 4, section 4, and that's it. Thank you.